key to being successful here is just to recognize the derivatives of functions and just back up. You can always, if you're off by a constant, you can always alter a little bit to make things work. So here we're told that the derivative of y is secant squared, and we want to find all possible functions that y could be. Well, we know that the derivative of the tangent is the secant squared, so y could be the tangent of theta. That works. And corollary 2 says if any other function had the same derivative, it would only differ from that function by a constant. So there's all possible functions. You can always check by taking the derivative. The derivative of the tangent is the secant squared. The derivative of constant is 0. So we've got it. Let's see. This is also theta to the 1/2. Of course, we know that when you take a derivative, the power decreases by 1. So if you undo a derivative, the power ought to increase by 1. So I would guess that this ought to be theta to the 3/2. But when I check that, I get 3/2 theta to the 1/2. That's close. I'm only off by a constant. I need something to eliminate that 3/2. So, well, 2/3 would eliminate the 3/2, and if I had had the 2/3 there to begin with, when I took the derivative, the 3/2 would come down. That would make 1, and I'd have theta to the 1/2. Are there any other possibilities? Well, corollary 2 says if there are, they could only differ by a constant. So there are all possible functions whose derivative is the square root of x. So it might be nice to write those with a root. So we could say that's 2/3 of the square root of theta cubed plus c, or you could also write it with the power outside the root, so the square root of theta cubed plus c. Alright, those are just different ways of writing that answer. I thought since they gave us a problem with a square root to begin with, maybe we should give it back. I guess maybe one more thing we could do is call it 2/3 theta times the square root of theta. Since if you have the root of theta cubed, you'd have root theta times root theta would make theta, and then another root theta. So there's yet another way of writing exactly the same function there. Put that in. This we recognize just a combination of the two. All we have to do is find a function whose derivative is this, and we can see that 2/3 theta to the 3/2, the derivative of that is going to give me the theta to the 1/2, and then minus the tangent of theta. The derivative of that is going to give me the minus secant squared. Corollary 2 says any other possibility could only differ by a constant, so that has them all in 1. Okay. This is really a question about finding antiderivatives because we're given the velocity. We know that the velocity is the derivative of the position, right? So usually we use s to stand for position. Okay, so we know that the derivative of this function s is 32t minus 2. Well, what function would have a derivative that's 32t? Since we have a power of 1, if we undo a derivative, the power should increase up to t squared. But if I take the derivative of that, that'll be a 2t. I need 32, so half of 32 is 16. If I put a 16 there, then the 2 will come down, double the 16 and give me 32, and then I'll have t to 1 power less. To get a derivative that is minus 2, then I would need a minus 2t. So s of t should be 16t squared minus 2t. And corollary 2 says any other antiderivative would just differ by a constant for that function. So there we go. Now, if you think about it, if you only have someone's velocity, then you can't really tell where they end up unless you have some information about where they started. So, for example, if I told you I drove for an hour at 75 miles an hour, you'd have my velocity, but you wouldn't know where I ended up until you knew where I started or where I was at some point. Then you could figure it out. Same thing here. If they told us that at time 1 our location was at 15, then we could determine the position. Until then, we have this arbitrary constant and we're not sure. But here's how to choose the constant. Okay, so this is if we were given some initial data, just a reference point that would start us off so that we could use that velocity to figure out where we went. Let's see, according to what we found just by taking antiderivatives, s of 1 should be 16 times 1 squared minus 2 times 1 plus some constant c. On the other hand, we're told that that should be 15. So 16 minus 2 is 14. So 14 plus c should turn out to be 15, and therefore c should turn out to be 1. With this initial data, now we can find the position, 16t squared minus 2t plus c, where in order to satisfy this initial data, then c had to be 1. Good. So if you only have the velocity, the best you can do is find the position up to some constant. You can think that constant is just there because there's not any certainty about the position at any time. But if you have some information about where you are at one time, then you can figure out exactly where you are at any time. Here's one more example. Again, we have the velocity. This function has a little bit of trouble at -2, so let's just assume that t is greater than -2. And we have some information, some initial data, right? We know that at time t equals -1, our position is 1/2. So this is key. If we know the velocity and we have some information about where we were at one time, we should be able to figure out where we are at any future time. Remember, the velocity is the derivative of the position, so really we know that s prime of t is t plus 2. Now we ought to ask ourselves, what function has that kind of derivative? Well, I notice that the derivative of what's down here, t plus 2, its derivative would be 1. So we have the derivative of a function over the function. That's the pattern that usually arises when you have a natural log. So I'm going to guess that s prime of t is equal to the natural log of t plus 2 plus some constant. Now I can check it. The derivative of the natural log of t plus 2 would be the derivative of the inside over the inside, which would be 1 over t plus 2. So yeah, that works. Now we just need to figure out what is that constant c. From what we've just found, we know that if you plug in 1, you'd get the natural log of -1 plus 2 plus c, which would be the natural log of 1 plus c. And the natural log of 1 is 0, because the exponent you put on e to get 1 would be 0, so we have 0 plus c. On the other hand, we're told that when you plug in -1, you're supposed to get 1/2, and this basically tells us that c has to be 1/2. So now, if we only use the velocity, then we could find our position up to some constant. Now that we had some initial data, we can find our exact position at any time, because we had a starting point to begin with.